We've applied line integral to segment A, we got 1/3, right? We've applied line integral to segment A, we got 1/3. Now, the same way I applied to segment A, I'm going to apply to segment B and segment C. But I want you to know that we have different approach to solve this Green's theorem. Question like this, we have different approach to implement it. The first one we did was we make use of parameterization. We make use of what? Parameterization, meaning I'm making use of what? Formula. Looking at this microscope is something that I can know the parameter of x and the parameter of y. You know, the purpose of me using the formula I used previously was to know the function of x and y, right? Now, looking at this closed curve is something that I can determine the function of x and I can determine the function of y without using the formula of parameterization, meaning without using x equals to x1 plus t all into bracket x2 minus x1. Similarly for what? Similarly for y. So what this means is that using I'll say shortcut, right? I'll say shortcut because it's actually easier. It's actually easier compared to what? Parameterization. And for parameterization, it doesn't really work for all questions. It works, but it is technical. It is technical. So this approach is actually easier. So I would want you to implement this approach to any given question. Though you can also implement parameterization, just have the idea on how parameterization works and have the idea on how this also works. Meaning, in this case, this approach, by the time I apply it to this curve, I'm going to get the value of segment A, same segment A, to be 1/3. And same approach, I'm going to get the value of segment B, and I'll get the value of segment C. Using same parameterization, you get your answer. You get your answer. But let's see. Now, for segment A, okay, now the condition, take note of this condition. How to determine your function of x and your function of y using the shortcut approach. Or you say using another approach. Now, from here, the first one is if any coordinate, the first condition, if any coordinate is changing, it becomes t. If any coordinate is changing, it becomes t. If it is not changing, you have it as the value. All right, I'm going to explain what it means. We said this first condition is that how do we see our function of x and y from the graph itself? We said the first one is that if it is changing, it becomes t. If it is not changing, it becomes that value that is not changing. You know, what I did previously, I make use of formula to get the function of x and y. Now, say segment A, and it is this approach I'm going to use to solve for segment B and segment C. Now, from here, for this segment A, of course, I'm having 0, 0 and 1, 0, just like the way we've seen previously. This is x, this is y, this is x, this is y. Now, I'm moving from A to B. You observe that along A to B, x is changing. You observe that along A to B, x is changing. Y is not changing, meaning at this point, this is A, this is B. X is changing from 0 to 1, then y is changing from 0 to 0, meaning y is fixed and x is what? Non-fixed, right? So that's what we are saying. We are implementing just like it's actually the same thing but different approach. Now, in this case, it's actually the same thing, but the difference is that you are not making the formula. So in this case, the one that is changing becomes t, the one that is not changing becomes the value that you have. Now from here, x is changing, meaning x equals to what? T. Then y is not changing, meaning y is equals to 0. It is 0 because it is still at the beginning, at the starting point, it is 0. At the ending point, it is 0. In a case whereby I have 1, I also have what? 1. X is changing, t. Y is not changing. So instead of 0, I have what? 1. So if the value is constant, you still have that same constant value. So for this case, I have 0 and I have 0. Therefore, y is equals to 0. Can you see that is actually easier compared to the formula method? So from here, calculate your dx. The x is equals to what? The t. Then from here, the y is equals to what? 0. This is my x, this is y, this is the x, and this is what? The t. Now, how do we get this limit? How do we get the limit? How do we know the lower limit? How do you know the lower limit and the what? Upper limit? Now, how it works is that your lower limit, it is your starting point, while your upper limit, it is the ending point. Now, come back to this line, which is C1. Okay, this is A to B. In this case, my A. Okay, now, just know that the coordinate, just like the way we explained previously, I want to know my lower and upper limit. The value, the coordinate that is not changing, the coordinate that is not changing, meaning the non-fixed, becomes your limit. That's what you use to determine your limit. But the main idea or the explanation behind this is that when you are starting, takes the lower limit, then when you are ending, takes what? Upper limit. So meaning, if x is not changing, at x, when x is starting, it's starting from what? 0. When it is ending, it's starting from what? 1. Meaning my lower limit is what? 0, and my upper limit is what? 1. Just like the way we've done previously. Now from here, your formula for line integral, which is integral Pdx+Qdy, right? Then from here, P is given to be x squared plus y squared, and Q is given to be x minus y. Now substitute. You have your limit to be 0 to 1, all into bracket your P, x squared plus y squared dx plus your Q, x minus y dy. Substitute your parameters, meaning 0 to 1, all into bracket t squared plus what? 0 squared. What's your dx? dt plus your x is what? T minus your y is what? Your y, 0, right? Then what's your dy? 0. This cancel out. You then have integral 0 to 1 t squared dt. Integrate, meaning t cubed over 3. Introduce your limit 1 to 0. 1 cubed over 3 minus 0 cubed over 3, which is equals to what? 1 over 3. Now you see that this is actually easier compared to the first one that will make use of the parameterization formula. So what we are saying is that instead of using your parameterization formula, you can actually work it out like this, understanding the concept. And the concept is that the one that is changing takes t, the one that is changing becomes t, then the one that is not changing remains that value, remain that constant value. So y is not changing, meaning y is t0. X is changing, it takes t. Okay, let me just say this. It's not all cases, because x is changing from 0 to 1. So you are saying t. You see the same thing as you saying 1 multiplied by t. In a case whereby x is changing from 0 to 2. X is changing from 0 to 2. The question is, will I still have x to be t? The answer is no. It becomes what? 2t. In some questions, not all cases, you have it as t. Just understand, if it is changing from 0 to 1, you have t. If it is changing from 0 to 2, you have x equals to 2t. What if it is 3? Let's say you have 3 here, meaning you have what? 3t. Then the limit becomes what? 0 to 1. You know, for our own question, my limit is what? 0 to 1, because x is changing from what? 0 to 1. But let's say this was the question. My limit in this case would be what? 0 to 3. Or let's say I have 2 here. My limit will be what? 0 to 2. So what we are saying in essence is that, whatever coordinate that is changing, say 0 to 2, 0 to 1, 0 to 3. If it is 0 to 1, if it is x coordinate that is changing, meaning x is equals to t. Okay, let me use x coordinate to explain. Let's say, for instance, x coordinate is changing all through. Let's say it is changing from 0 to 1, meaning x at that instance becomes t. How do you get t? 1 multiplied by t. Let's say it is changing from 0 to 2. X becomes 2t. How do you get 2t? Meaning 2 multiplied by t. Let's say it is changing from 0 to 5. How do you get? Let's say it is changing from 0 to 5, meaning x is equals to what? 5t. How do you get 5t? Meaning 5 multiplied by what? T. So that's the whole concept behind it. Alright, back to our own question, which is what? 1. So I have x equals to what? T. So I have my limit as this. So what I'm trying to say is that this approach is actually easier compared to the parameterization formula. Start using a formula which is x1 and x2. So this makes our work easier. No stress, right? Alright, let's solve for segment B. Let's solve for segment B. Let's solve for segment B. Same way we solve for segment A, nothing is changing. Just apply the same concept. Just apply the same concept. Understand the principle. Once you understand the principle, you apply all through. Now for segment B, for segment B, what's my movement? I'm moving from B to C, meaning I have 1, 0, then 1, 1. Now from here, this is x, this is y, this is x, this is y, right? In this case, x is fixed. In this case, x is fixed, right? Then from here, y is changing. Since x is fixed and it is fixed with a value of 1, meaning x becomes that 1. Are you know what I'm saying? Just like we explained previously, x is fixed with a value of 1, meaning the function of x is still 1. So you are saying that x is equals to what? 1. And y is equals to what? T. How do you hear this T? 1 multiplied by T, right? Meaning it is starting from 0 and it is ending with what? 0. And we said the one that is changing takes T. Not just T in all cases. Let's say you have 2 here, meaning 2T. But in this case, I'm having what? 1. That is 1 times T. Alright? So in this case, y is changing from 0 to 1. So I have what? T. Now, differentiate the x is equals to what? 0. And the y is equals to what? The T. Any question on how I got this? Your normal differentiation, say the y over dt is equals to what? 1. Cross multiply. Meaning the y is equals to what? Dt. That's what we did. So we said the y is equals to what? Dt. Alright, now from here, we said this is my function of x and y, then I've differentiated. I got the x to be 0 and I got the y to be what? Dt. Alright, now from here, how do you know your limit? Your limit, the approach to know your limit is actually what? Easy. We said your starting point becomes your lower limit, while your ending point becomes your what? Upper limit. Now, since y is changing, just like the way we've explained for parameterization. Since y is changing, meaning the what? Non-fixed. So I'm starting from 0 to 1. My limit becomes what? 0 to 1. So if you want to write that in a proper way, you say T is an element of 0 to 1. T is an element of 0 to 1. But this means the interpretation for this is that you are starting at 0, then you are ending at what? 1. So generally, when you are starting, takes the lower limit. When you are ending, takes what? Upper limit, irrespective of the what? Value you have here. Okay? Now, this is for segment B. Let's apply my line integral formula, which is integral P dx plus Q dy. I know that P and Q, they are constant, which is x squared plus y squared dx plus x minus y dy. Substitute what you've gotten so far, meaning integral 0 to 1, all into brackets. This is x, right? Meaning 1 square plus what's your y? That is t square, right? What's your dx? Dx is what? Dx is 0 plus all into brackets. What is x? 1 minus what's y? T multiplied by your dy, which is what? Dt. Then this cancel out, right? So you have integral 0 to 1 minus t dt. So from here, integrate, apply your normal integration. This is t minus t squared over 2. Take your limit. This is 1 to 0. Substitute 1 minus 1 squared over 2. Of course, to be what? Minus 0. By the time you substitute 0 into this, you have everything minus 0. So from here, let's evaluate. Meaning I have 1 minus 1 over 2 minus what? 0. By the time we take the LCM, let's take the LCM of this. This means 2 minus 1, which is equals to what? 1 over 2. So for segment B, I got 1 over 2. If you apply parameterization approach, you definitely get 1 over 2. You get 1 over 2. I've actually done that. Okay? If I apply parameterization formula, you definitely get 1 over 2. You definitely get what? You definitely get 1 over 2. Alright, now for segment C, I'm moving from what? 1 to 1, 1. My coordinate is going in this manner, 1, 1, then what? 0 to 0, meaning this is x, this is y, this is x, so this is y. Now, applying the same idea, from here, you observe that for your segment C, both x and y coordinate, they are changing, meaning they are non-fixed. X is changing, y is changing. And we said that since x is changing, meaning any coordinate that is changing or any vertices that is changing takes what? T. You represent it as what? T. So x is changing, meaning that x equals to what? T. Y is also changing, meaning y is equals to what? T. So this is the function of x and this is the function of what? Y. Now differentiate. You have the x is equals to what? The t. You have the y is equals to what? The t. Now, how do you go about your limit? We said whether you are starting becomes your what? Lower limit. Where you are ending takes your what? Upper limit. Now, I can use any of these coordinates. Be it x coordinate or y coordinates. In both of them are changing. So let's say you are using x coordinate. I'm starting with 1, my lower limit. I'm ending with 0, my upper limit. Similarly, if you want to go with y, I'm starting with 1 and I'm ending with what? 0. So meaning I have what? 1, 0. Then writing this, you see this as t is an element of what? 1, 0. So this is what it means. Now, applying your line integral formula, meaning integral p dx plus q dy, as we know that p and q, they are always constant. P and q are constant, meaning you have what? Integral, all into brackets, x squared plus y squared dx plus what? What's your q? X minus y dy. Substitute each function. You have 1 to 0. Your x is what? T, meaning t squared plus y is also t squared multiplied by the x. The x is what? The t plus t minus t dt. Then t minus t meaning 0. 0 times this will cancel out. You are left with what? 1, 0 and 2t squared. This plus this will give you 2t squared. Now integrate this. Okay, before integrating, factor out your constant. This implies that you have 2 integral 0 to 1 and t squared. Now integrate this. This will give you what? T cubed over 3. Substitute your limit 1 to 0, meaning that you have 0 all cubed over 3 minus 1 cubed over what? 3. And this will give you what? 0 minus 1 over 3, which is equals to what? Negative 1 over 3. Not forgetting that you have a constant value here, which is 2, meaning 2 multiplied by negative 1 over 3, and this is equals to what? Negative 2 over 3. So when we applied the line integral to segment C, we got negative 2 over 3, meaning you are actually done with this. The last step is that add up all values that you've got, meaning for segment A, segment B, and for segment C. For segment A, I got 1 over 3. Segment B, for segment A, I got 1 over 3. Segment B, I got what? 1 over 2. And segment C, I got negative 2 over 3. Therefore, I have 1 over 3 plus 1 over 2 plus all into brackets negative 2 over 3, meaning 1 over 3 plus 1 over 2 minus 2 over 3. Take LCM. What do you have? 6. 6 go here. You have 2 plus 3 minus what? 4, right? This is 5 minus 4. That's what? 1 over 6. So you are saying that when you apply line integral, which is integral p dx plus q dy, which is equals to the line integral of c1 p dx plus q dx plus q dy plus the line integral of c2 plus the line integral of c3. Meaning, when you are saying that when you apply the line integral, which is equal to the line integral of C1, when we say C1, meaning A to B, which is what we represented as segment A. When we say C2, when we say C2, meaning B to C, which is represented as segment B. Then lastly, when we say C3, meaning what? CA, which is what we represented as segment C. And from our orientation of our movement, you can see that we denoted it as C1, C2, and C3. So we are saying that this line integral, when we added it up, we got 1 over 6. We got 1 over 6. To now show that this question verifies Green's theorem, you must, if by the time you use double integral, and you are getting 1 over 6, it means it verifies Green's theorem. If otherwise, it does not verify Green's theorem. I'll be dropping the link below. I'll be dropping the link to the description below for the double integral of this question. Meaning, by then, if we get 1 over 6, it means this our question verifies Green's theorem. If we are not getting 1 over 6, it means this question does not verify Green's theorem. So now, you've seen that you can use different approach to solve your Green's theorem. You can use the formula method, which is what we call the parameterization, and you can use the shortcut method, which is actually easier. From your graph, you determine the function of x and y for whatever segment you have for each segment. So, we'll be dropping the link. Also, we'll be dropping the video on this particular question. We will use parameterization to solve this particular question. We will solve for segment C, we will solve for segment B of this same question, and we will solve for segment C of this same question using the parameterization approach. You will now see that we'll be getting 1 over 2 for segment B when we use parameterization, and we'll be getting negative 2 over 3 when we use parameterization. So choose the one that suits you. But I'm going to advise that you should make use of this, since this is actually easier and it's easy to comprehend. So I would want you to employ this. But also know how parameterization works. All right.